All right. Like usual, every time I say this, we'll be on the UBIT and SUBIT.
Okay.
Yes, we were putting together methane. Now, methane is a gas that's produced naturally. It's got a common name. Does anybody know methane's common name?
HC.
It is known as calfart or swamp gas.
Oh.
Calvars.
Cows are one of the great producers of methane, believe it or not, and so are just the natural swamp gas. And all it is bio stuff degrading. That whole fiery swamp thing, that actually does exist. Where enough gas can be emitted from the ground that it can actually be on fire.
Good.
Well, methane is very combustible. I hope you can see, first of all, is there a metal involved here? No metal involved. And I think you can see, since it's no metal involved, we're going to be sharing electrons. I think you can see, we know that hydrogen only needs 2 to be happy. And then you got nice 4 little spots open here. This would be an easy share. These 2 electrons, these 2 electrons, these 2 electrons, and these 2 electrons. If we share them, everything's happy. Now to clean this up, how do we show a shared pair of electrons?
Give it a wedding ring.
The dash.
The dashes. And this would be the formula, structural formula. It shows how these bonds are bonded together. And who would give me the chemical formula for this? From what you see,
CH4.
it would be CH4.
Wait, I understand.
Nuh-uh.
Yeah, because there's 20.
All right, these are all single covalent bonds.
Nuh-uh. I have it written right here.
And so we already know that there is a different way for bonds to be, and those are our 2 examples. Hint. Well, it's a good hint. Hydrogen can only make single covalent bonds. Which makes perfect sense. Hydrogen can only make single covalent bonds. Now we'll get to a place where if hydrogen is acting like a metal, but we'll be that's clear. It will be very clear at the end of this class. But hydrogen is clearly not a metal. And so when it's in a molecule, it will only make single covalent bonds because it can only have 2 electrons. All right, any questions here on methane? I think it's hopefully straightforward. Yes?
If you wanted to write can you write that in one line? Like
This one won't be linear. You will be able to see ones that you can see in one line, but really the only way to show this structure is to have it coming out of the 4th quadrant. Yeah, you'll find out in organic chemistry that the C's and H's get so long that they'll just put like a CH2 like this. This will do this. Because they'll be bonded to long chains of carbon. But that's organic chemistry. To show its full structure to this point, that's probably the best and easiest way to do it.
Thanks.
All right. Well, if there's a single covalent bond, and I know that there's multiple bonds, my guess is there's going to be what? Now, we've kind of already seen a double covalent bond. I know that you've been reviewing your notes. Who can tell me the first one we've actually seen already?
Table salt.
Incorrect. That would have sodium in it. That's a
Hydrogen peroxide.
Oh, yeah. H2O2? Is that what you're talking about?
I've actually shown it, like I drew it. Ooh, who said that?
Me.
Briella said that?
Oxygen? I said oxygen.
Oxygen.
Whoa! I totally guessed. It's okay.
Oxygen was already drawn on the board. Hey, real quick, oxygen is in group 16, so how many valence electrons? Now,
6, 7. Oh my god.
no, that would be oxygen and a halogen. This is what I've already drawn in your notebooks. If an atom has 6 and it wants 8, how many does it need?
2.
It needs 2 more. Well, both of these oxygens have 6. Both of them need 2 more, and the only atom to get them from is that other oxygen atom. So to draw this, we actually say, hey, if you share these 2 with me, I'll share these 2 with you. They both go into the bond. That's a total of how many electrons in the bond?
8.
That is 4. And that means we need a double dash.
Oh, double. Oh.
Now. And that leaves 4 unpaired electrons, well, 4 unbonded electrons, sorry. 4 unbonded electrons on each oxygen. And notice, if we count around each atom, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. This is a very happy molecule. In fact, O2, the molecule, makes up roughly about 19% of the air you breathe.
Yay!
Very stable molecule. Yes, Sophia?
Would you just like cancel it out?
Whoa, cancel out.
Well, like whenever you you combine like the little dot thing, the 2, like you made it into a line, and then like kind of cancel.
Well, that's because the lines, you gotta remember, we have already written up here that a dash, 1 dash, that holds 2 atoms together represents a shared pair of electrons. But it's telling you that they're held together by sharing. So this is the hydrogen molecule H2. The reason I put 2 dashes here is not to make an equal sign.
It's because they can only.
That's a shared pair, and that's a shared pair. This part of it's not math. Those are not equal to each other. All right. So let's do another example. A double covalent bond. Let's get that definition down. This is a covalent bond between 4 electrons that are shared between 2 atoms. That is bad wording. We can correct that. Is a covalent bond where 4 electrons escape.
Escape?
No.
Stop.
Oh, that's
Mm-hmm.
Where 4 electrons are shared. Who wrote these notes?
You.
Oh, that's true, I did. Alright, that's better. This is a covalent bond where 4 electrons are shared between 2 atoms, or 2 shared pairs of electrons. Excellent. Much better. Looked like some lysdexia going on there.
That would.
It was a joke.
Covalent bend.
Whatever. Don't they use it to preserve like?
They used to. Some people, some labs consider to use some formaldehyde. Formaldehyde, though, has been found to be carcinogenic. So
Like when we it's used to preserve.
formaldehyde can be used as a preservative.
But it causes cancer.
You guys know that ad with all the creepy like taxidermy things talking about formaldehyde?
What?
Oh, yeah.
Yes. I didn't know
W
that.
ad.
They always on my
I don't know what you're talking about, but that's okay.
It's like an
It,
ad that
it
plays.
like zooms in on like a deer's eye, and then it zoomed in on some other taxidermy stuff. And then like formaldehyde is preserving this, but it's bad for you. It's like really.
Gotcha.
It's
Oh,
Well, anyway, this is its chemical. Now, the reason I choose formaldehyde, the reason I choose formaldehyde is that it gets a little more complex, but if you use the rules I've already written right here on this page, then we can actually start to build this one up pretty good, okay? So let's get all of the atoms out here and their Lewis dot structures. How many hydrogen atoms do I have to draw?
2.
2. And we already know its Lewis dot structure, H with 1 dot. Carbon atoms, how many do I have in this formula?
1.
1. So I got to put down a carbon. And then lastly, an oxygen atom is also present. All right, so oxygen, how many does it have? How many does it have?
Or 8.
Why would it have 8? Oh, it's filled.
No,
It's in
just kidding.
Group
16.
16.
I was looking at it wrong.
6.
I said 6. I said 6.
I know you did.
I was looking at the number.
But I had people saying 8,
Why were you,
16.
why were you trolling me?
All right, let's go over that one more time. Group 1, all have 1. Group 2, all have 2. Group 13,
Has 3.
Group 14,
That's 4.
Group 15,
5.
Group 16,
6.
Group 17,
7.
and then finally in Group 18 they all have
8.
and that's why they don't make bonds.
Oh,
Alright, so now when I ask these questions, we don't have to say the wrong numbers anymore. Now, we know, according to this note right here, this nice hint, hydrogen can only make what type of bonds?
happy.
So,
Happy.
the questions will always be, okay, where do we put these atoms?
You put it in a lot of ways.
Now, these guys can fit in interesting ways, but I'm gonna show you one that I think should help do this. Look, if we stick these hydrogens on oxygen, that will work. Except the problem with that is that actually both hydrogens will be happy and the oxygen will be happy, and in fact that's called H2O. What that doesn't make happy is the carbon. So in other words, yes, we could stick the hydrogens on the oxygen if we wanted, but that makes a different molecule altogether. We know that this molecule exists. Why? Because Rhett saw a commercial. So, how do these atoms then go together? We're not going to stick them on the oxygen. Now, we could stick one on each and see what we got left over, but that's going to be kind of an odd thing. Now, if they were both the same atom, like this was a carbon and this was a carbon and these were all hydrogens, I would be all for breaking them up and sticking them on there. But since I know I don't really want to put them on the oxygen,
2 of the carbon next to oxygen.
I like throwing 2 of them on the carbon and then we can see how this goes together. So that was a good suggestion, Sam. I like it. So I'm going to go ahead. I know that we can go ahead these two, and I'm going to stick them together. So right now I have carbon with 2 single covalent bonds, because that's all hydrogen can make. That leaves me with how many unpaired? 2. And I still have this oxygen molecule, atom, with its 6 valence electrons. Now, if I count around each atom, I get a happy thing. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. They both have 6. They both need what?
2.
They both need 2. And wouldn't it be nice if they said, hey, you share these 2, I'll share these 2, and we'll all be happy. Who can clean this up now for me on a proper structural formula? Tell me what to write.
H2CO.
H. What do I write next?
4. 2, 4.
Two.
One of those.
No, not the formula. I need a structure.
Oh,
Dash.
4.
H dash,
There.
C.
4.
The double dash.
double dash,
Four electrons are added.
4 dots.
4 dots here.
Then a line going above the C. Another
And
H.
an H.
Oh, that is beautiful.
That looks like H minus C to the H
If you count
equals
around
0.
every atom, they all have the satisfaction of
What am I
8
looking at?
electrons, except of course for hydrogen. 1, 2 for hydrogen, happy. 1, 2 for hydrogen, happy. 1, 2, 3, 4, 5, 6, 7, 8, carbon, happy. 1, 2, 3, 4, 5, 6, 7, 8, oxygen, happy. Everyone's happy. That is the structural formula of formaldehyde,
I'm not happy.
and
Very not happy.
it is H2CO.
Where did we get that from?
Oh. Hi. Oh, now it's pretty. Okay, there. Wait, that's literally.
It sounds like ugly.
That's what Bennett said.
It's also
Scam.
You're listing
Scam.
And yes, there is occurrences where triple covalent bonds do take place. Without me hitting the next slide up, who can tell me the note that you would write down for a triple covalent
What's it
bond?
called?
covalent bond.
Yes,
Or
Sophia.
6.
Oh.
What was the question?
Oh my gosh.
You got this one.
Girl, what's the next note?
Triple
That's
covalent.
gonna
What do
go
you
down.
think it is?
Triple covalent bond.
Acetylate.
It is probably example ... and then
Wow.
a 2 in it.
Okay.
Yo, Taylor knows it.
A 4.
Taylor don't know it.
He's asking
That was
us
a
to
good
do-
try.
Hey, good try.
Elijah.
It'll be where a covalent bond. This is a covalent bond where 6 electrons are shared between 3 atoms or 3 shared points. Right?
So like,
Between how many atoms?
3, 2.
is
Oh.
it 2 and 4?
6 electrons shared between 2 atoms.
Hold on.
That was close.
You were
There's a 2 in there.
there. You did say the number 2.
She
Oh,
said,
there's 3 pairs.
yeah.
You finally
I know, guys. I predicted
I've done
it.
something.
Sure.
Keep that performance up.
Okay, you can do this.
I do like all efforts.
Yeah, if
Thank you.
He probably doesn't even have tokens.
Jack.
Could you write formaldehyde as COH2?
COH2.
Like, why is it in that order?
Yes.
because it's that way.
So yes, you could, but we're going to find out why the hydrogen often, especially in non-organic chemistry, and although formaldehyde does have carbon in it, I would not fully classify that as an organic molecule.
Okay.
Sure.
But you'll find out why at the end of this class, actually, on why we usually put the hydrogen first.
Is there a quadruple covalent bond?
Oh!
Or does it stop at triple?
High five!
Elijah's on a roll.
He is. That would be the great question because it makes sense. They would both have 8. Everyone would be happy.
No.
And the problem is that in order to share electrons, here's one of the big differences, and I'm glad the question was asked. We should be listening, not chatting. Ionic bonds stay together because opposites attract. Positive, negative, stick. Like a magnet. Got it? Covalent bonds stick together because they have to actually come close together to share these electron clouds. So they come together to share their electrons. The problem when you get to single covalent bond, we're going to write this note down so you don't have to write it now. Single covalent bonds have to come close together because they're sharing 2 electrons. Double covalent bonds actually have to come closer together because they're sharing 4 electrons. Triple covalent bonds are really getting close together because they have to share 6 electrons. The problem is when you try to do 4, the atoms get too close together. It's called sterically hindered. They can't bring the nucleus close together, they can't overlap enough electron clouds together, and so there are no, and I don't even think even in a lab that we forced it to happen, because we can force a lot of things. But I don't know of anything on record of making an atom like carbon
Then I'll be the first.
Making an atom like carbon, slam it together. Maybe if you go down group 14, you might be able to do this to get it to do this.
Oh,
God.
I mean,
possible.
in your brain, it could happen.
Become the same atom.
But, again, we don't believe, at least that I have not read
Everything's
anything on that. The best chance you have is going down group 14 where you got big atoms. You might be able to get it to do it and say, hoo-hoo, I've done a quadruple covalent bond. And you would write a big paper and you get a pat on the back. It's not Nobel Prize stuff, but I think it would be probably pretty good. Yeah.
Aw.
If they got too close together, like trying to do a quadruple bond, would it become like magnesium through like nuclear fusion? Or is that just not how it works?
Yeah, no,
Right.
I get what you're saying, but no, that's. So let's do ethine. Carbon. I'm not making these up.
Are you sure?
Hydrogen. C2H2 is an actual organic molecule. Now this one has 2 carbons and 2 hydrogens. That off the bat, and I also can give you this hint for organic chemistry. We're not going to talk about organic chemistry until the very end of the year. Okay.
I wasn't. I think I was just
Okay, well, fiddle, no. Thank you. Let's put it away. Somebody tell me what you would do to at least start this one off. Bennett.
You would connect one hydrogen to one carbon and the other hydrogen to the other carbon.
Yeah, that, look, when you have equal amounts of both, I like that starting point. Let's attach them together. And remember, hydrogen can only make single covalent bonds. So we have this left. And we got another C that looks exactly the same. And now, if I count around this carbon, 1, 2, 3, 4, 5, wait, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, they both need how many more?
2, 3.
They both need 3 more. And wow, isn't it nice? They all have 3 to give one another. So this would 3 into the bond, these 3 into the bond, and that is 6 electrons being shared between these 2 carbon atoms.
Wow.
Everyone's happy. Each hydrogen has 2, and the carbon, if you count around it, has 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Both carbons are happy. Word
Don't you have to like make it?
to your mother.
Literally, because they're watching.
You've already written that down.
Wait.
It just said single covalent bond again. And as promised, I said you would take the note. The length of these bonds, I already told you, differs. A single covalent bond is greater than a double covalent bond, which is greater than a triple covalent bond. So get that note down.
Wowzers.
What time of day is it? 9:16.
Maybe 10, 16. So, 2 later.
Does it end at 30 or 20?
30.
So bond length is the length of a covalent bond. It's just the distance between the 2 bonded atoms. Single is the longest of the bonds. Triple is the smallest. And that again, as we already described with Elijah's question, is the reason quadruple bonds don't exist. They're too close together. let's see if your brains are off this idea of just getting the note down. Remember, this is why we have to practice them at home. Getting the note down is important. Getting it down correctly, important. Putting it in your brain, absolutely more important. Who thinks they can, first of all, tell me the definition for bond energy. And then give me the trend for bond energy. I know Rhett's not going to be asking or answering this question. What would you like to do, Rhett?
Bathroom.
You may go to the bathroom. All right, Jack, what do we got?
I'm guessing it's something to do with covalent bonds and how much energy it takes or is used to like bond to atoms.
I like it. It's the energy needed to break the bond.
Break a bond, not form a bond.
Good. But in this sense, it's also going to be the energy that's kind of stored in that bond.
To the camera.
So, I like it. Energy needed to break the bond between the two atoms. Who thinks they can come up with a general trend for which is greater than what? And maybe give me some reasoning.
Is it linked with ionization?
No, let's just do this. Take your two fingers, go like this, link them together, and pull. That's pretty good. That's not going anywhere. I'm a pretty strong dude, right?
What do we do?
But take two fingers, put them together, and now pull. Does that feel at least a little stronger? And now just take all your fingers, put them together like this, and then pull. Well, guess what? Same thing for atoms. So, in other words, the more you overlap, single is going to be the least energy storage, energy needed to break it, whereas triple, because of all of that overlap, it's going to be the hardest bond to break.
Because like they're closer together. So
They are, like, they have a lot of overlap, and they're holding on tightly. So that means there's a lot of energy stored up in those bonds. And let me show you one of these molecules and give you a nice little thing. And then we got one more slide and we're done today. I want to do the nitrogen molecule. All right, you guys walk me through the nitrogen molecule, because although oxygen is very stable, nitrogen actually makes up 79% of our atmosphere. So it's very stable on Earth. So somebody walk me through this structural formula.
You have two nitrogen atoms, which are in group 15.
And
So you have five.
so I got two of these with 5 dots. They both need what?
They need three.
They both need 3 each. What kind of bond is this going to be?
a triple.
It is. Wow, you guys, this is awesome.
And that's
Wait, that's like easy.
So this is very strong bond. It's a very stable molecule and very stable. It takes a lot of energy to break that bond. But when you do break that bond and put nitrogen in other molecules, so I already showed you this one, TNT, trinitrotoluene.
Boom, dynamite.
This gets to a very stable place, a very strong bond, very stable on Earth. This is very high energy, not stable.
Hello.
This is the whole,
High to low. Boom. So it's
Can we do that in class?
Yay.
No, we.
boom! That's very stable, very, very stable, very strong bond, not easily broken. And when you do break it, you can then store store these high energy molecules. And when you store that energy in there,
Really?
and it goes to this nice low energy state, hard to break bond.
Can we have a test where it's
How
simply
would
just,
you
like, you're testing
make
to see if we know
that?
which one goes higher?
Just curious.
Yeah.
The answers are just blue.
Yeah. Yeah. How could we like make that?
Just, yes. Believe it or not, this concept, we've seen it, I don't know how many times already this year. All right, the last part for us to understand our homework is to name these things. And again, you're going to have this lecture online so you can review it over Thursday and Friday as you do your work. So, first of all, ionic compounds. They're not hard to name. The positive ion always goes first. And that's 95% of the time what? The positive ion is always a what?
First.
What? Very good.
Yeah.
The second ion is where you change the name.
Naming compounds.
The second ion, you drop the ending and add an IED suffix, unless it's polyatomic, and then you just put the polyatomic ion down.
Duh.
And we already know this. You guys don't realize you were doing this, but you do know this already. Now, we can call that table salt, but you guys even call it what?
Sugar.
Say that again.
Sugar.
Sodium chloride. Notice,
Right again.
the metal ion goes first, sodium, and then you change chlorine, drop the ending, and add IDE. So you guys have been calling this sodium chloride, which is actually, it's a scientific name, forever, or table salt. Now, according to the note we just wrote, what is the name of this salt?
Nano.
Oh, sodium.
Nanolide.
Nitrate.
Nitrite.
Salt.
Sodium.
Nitrate.
Nitrate.
I suppose.
Because NO3 is the nitrate ion, you don't have to change that ion, but be careful, what you just said was this.
Oh, what did I say? What?
That's sodium nitride.
Oh. Whoops.
Sodium nitrate, sodium nitride. Why? Because that's with nitrogen. You drop the ending, add IDE.
Try.
If it's polyatomic ion, you just write the
Can we
name
lick
of
it?
the ion.
Yeah, is that a lick it?
That's right.
Can we look at?
I probably wouldn't. Alright, there are certain metals. Silence you! There are certain metals that have to be identified by their charge. These are all the D-block metals: tin, lead, bismuth, polonium. Don't worry, it's not hard because you have a bonding periodic table of elements that you'll be able to look at. But does anybody remember how? Does anybody remember how to name these by their charge? You did this, you saw it at least when you were writing formulas.
How to.
Is that the one where you
Yeah, you remember the crisscross from last week? Yes, 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 that's good. But do you remember how you found the charge of certain metals?
I don't think that was in the video.
Sure it was.
Or remember.
I mean, part of it was actually.
Yes.
Like, part of it.
Well, here, let me give you the example. We'll do this one. So this is lead oxide, but when you look on your periodic table of elements at home, you're going to see that lead has two oxidation states. It can be a +2 or a +4. How are we going to know this? Well, we're going to know this, okay, by going through our nice hints for ionic bonds. 1, figure out the names of the ions. Well, that's lead and that's oxide. Yay! That's not hard. 2, is this metal a D-block metal or one of the ones with multiple charges? If yes, you need to use a Roman numeral. So that's what we have to do for lead because it has multiple oxidation states.
Oh, that's what we do. Is that the example from your the one on the board?
And then the total negative charge is the important thing, because once you find the total negative charge, that is how you can find your positive charge. Well, that brings me to oxygen. Oxygen only has one oxidation state, that's 2 minus. There are 2 oxygens. What is the total negative charge here? Total negative charge. If you got 2 oxygens, each at 2 minus.
The double covalent bond?
No. It can't be covalent. It's got a metal in it. Total negative charge. I got 2 oxygens, each at 2 minus.
-2 minus?
Well, that would be if I only had 1 oxygen atom.
So it'd be negative. Oh, yeah, so 4 minus.
All right, good. My total negative charge is 4 minus. How did we get that?
Please don't.
2 oxygens, each of them are 2 minus. Well, look, that total negative charge, there's only 1 lead atom. Remember, an ionic compound has to be neutral. So what does that lead atom have to be in order for this to be neutral?
More positive?
Very good.
Oh.
If that's total negative charge of 4 minus, the total positive charge has to be 4 plus. I distribute it over 1 atom, so this is going to be lead, Roman numeral 4, oxide. Excellent. And again, you just have to do those.
Your alarm's going off.
No.
Your phone's up here on the video.
It won't be going on.
It is, it's 9:30.
I'm looking at the time. All right. We will be getting towards the end of class, and so now I have to make sure. I like how you guys look. Man, you pack up faster than anybody. There's going to be numbers on these worksheets that you can do, and one. No. Keep them packets of 2. Packets of 2. You can stop.